All right, welcome to lesson 6.4, transformations of trigonometric functions. Today we're going to look at transforming trigonometric functions in the same way that we've transformed other parent functions. So we're going to focus on sine and cosine here. For tan theta, you would only be looking at really simple transformations. So you're not going to be looking at complicated transformations that involve a, k, d, and z. The focus here is definitely on sine and cosine. If you don't remember the effects of A, K, D, or C, I want you to go back and review them in previous units. So we definitely focused on that in Unit 1, but we've touched on it in all of the other units as well. So we've got a few methods, and I'm going to add a third method for transforming trig functions. For method 1 that you guys have seen before is doing a series of sketches. So you begin with a sketch of your known parent function. You're using those key points that you know from the parent function. You're going to sketch the stretches, the compressions, and the reflections second. And then your third version is going to be sketching the translations. So that's what I require to see. You can also step it out even more. So if you wanted to do this, like the vertical stretch in one step, and then the horizontal compression in a second step, and then do the reflections, and then the one translation at a time, you can do that. I don't care how many you show, as long as you show at least these three. Second method is mapping, which has been a favorite in this class so far. You're going to map the key points. So again, you have to know the key points, theta, comma, y for sine and cos, and then you're going to map them using our same general mapping formula that we've used before. Now this can be trickier for some people since it's going to involve fraction arithmetic. Remember that your theta values are going to involve pi by 2's, and you might be dividing those fractions by a k value. So that can be tricky. I'm actually not going to go over method 1 or 2 because you've seen it before. I think that you guys are pretty confident with that. If you need some help though, let me know. I'm going to focus on method 3. It looks super complicated here where I've written out the instructions, but that's just because it's a new method, right? So I really want to make sure that you know what to do. It's my personal favorite method for trig. I think it's the easiest. So box method, really quickly, we're going to draw a rectangle. You're going to find the vertical key values. So that's going to be your max, your min, and your middle axis number. Label them on the side of the box. Then you're going to find the horizontal starting point. So that's going to be based on your translation number D. Label it on the bottom left of the box. Then you're going to calculate the period. Remember that the end of the box is going to be the starting value D plus whatever the period length is. That might be hard to figure out mathematically because, again, it's going to involve some fraction math. You don't actually have to figure it out, the ending point, if you don't want to. You do have to calculate the period. The next thing we're going to do is find all the theta values for all of the key points. Remember that the first key point is at the theta value of D, the horizontal translation. The second key point is going to be at that starting point plus a quarter of the period. So I'm going to take the period and divide it by 4. And then I just continue to add that period by 4 to the last value that I just wrote down. I know it looks complicated, it's not that hard. I'm going to show you a couple of examples. After you're done that, you've got all the vertical values labeled, you've got all the horizontal values labeled. The next thing you need to do is inside the box actually draw the curve. So you have to think about, well, is it a sine curve or is it a cos curve? Remember, the sine curve starts on the axis and goes up to the max, then down to the min. The cosine curve starts at the max, then goes down and back up. Then you have to think about, well, is it a positive or a negative a value? So do I need to reflect that curve inside the box? And then the very last step, you've already got all the numbers you need. You just have to draw the final version. You've already done all the rough thinking. Just throw it on the grid and make it neat and tidy. When you do that, you're almost always asked to draw 2 full cycles. So make sure you leave space on your axis to draw the second cycle. Okay, so example 1. The first thing that we need to do for this function f at theta is state the transformations that were applied to the parent function. So we can see here that the parent function is sine theta, and we've got an a value of 2, a k value of 3, a d value of pi by 2, and a c value of 1. So we're going to interpret all of that in terms of what are the transformations. I'm going to start with my multipliers as always and end with my adding and subtracting. So the first multiplier, 2, is my a value. It tells me that there's a vertical stretch. And it's a factor of 2. The second multiplier, 3, is a horizontal. And remember, it looks like multiplying by 3 in the equation, so it's actually dividing by 3. So it's actually a horizontal compression. And the factor is 1/3. So we're doing the reciprocal of that k value 3. Next, we're going to take a look at, I'm just going to go in order. So I'm going to look at this d value of pi by 2. That's a horizontal translation, but in trigonometry, we call it a phase shift. So when you see the term phase shift, it's just another term for horizontal translation. And my phase shift is pi by 2 to the right. So don't forget to tell me how much and which direction. So make yourself a little note here. Phase shift is the same as horizontal translation. All right, the last thing, we've got that +1 outside of the sine function, so that's a vertical translation. And we're going 1 unit up. All right, part B of the same question. So we're looking at the same equation here. I just copied to the next page. We're going to show evidence of our method. So I'm going to use the box method just so that you can get used to it. Again, if you would prefer to use the mapping or sketching the different transformations, you can do that as well. I'm going to start by drawing the box just like they told me to in the method. So I'm just doing like a rough box. It does not matter. It does not have to be perfect at all. The first thing I'm going to do with the box is label the 3 vertical values. So I need to know where's the maximum, where's the minimum, and where is the axis. So remember the axis, if I think about my transformations that we just looked at, and I ask myself, like, what would change that horizontal line that's going through the middle of the curve? Well, if I stretch it out vertically, that's not going to change anything. If I compress it horizontally, that's not going to change anything. A phase shift, if I'm shifting that horizontal line left or right, that doesn't change anything. The only thing that changes my axis is that vertical translation. It's going 1 up. So remember, it used to be at a height of 0, but now I'm moving it up 1. So my axis is going to be the same as my C value at the end. Then I need to figure out the maximum and the minimum. Now that is going to be changed by that vertical stretch. Remember the vertical stretch, my amplitude of my regular sine curve is 1, but my amplitude is now going to be stretched or multiplied by 2. So the amplitude is actually the same as this A value out front here. So I'm starting at 1 in the center, and my amplitude is going to be going 2 above and 2 below. So 2 above, my maximum will be at 3, and 2 below 1, my minimum will be at -1. So all I did there, taking the C value and then adding the A value or subtracting the A value to find the min. All right, next, the horizontal stuff. A little bit trickier. We know that the sine curve and the cosine curve have 5 key points. So the start of the box, the end of the box, the middle, and then a quarter and 3/4, right? There are my 5 key points. I need to figure out what the numbers are. Well, the first one is easy. This is going to be my phase shift value here. So this is my starting point. So the starting point, and remember it's minus pi by 2 in the equation, which means it's going to be positive pi by 2 on the graph. So flipping that over. So I know I'm starting at pi by 2. Now the tricky part is coming up with the rest of these theta values or x values. So I'm going to now use my k value. My k value is going to help me figure out my period. Remember before, with a regular sine curve, the period is 2 pi. But I want to take that and compress it by 3 or divide it by 3. So I'm going to take my old period of 2 pi and divide it by the k value of 3. So I know now that the period is 2 pi by 3 because the length of the whole box here horizontally is 2 pi by 3. I could figure out the end value by taking my starting point pi by 2 and adding the period 2 pi by 3. That seems complicated. what we're going to do is figure out, well, where are the key points? Well, there's going to be a key point every period divided by 4. This makes sense because I took the box, remember, and I cut it into 4 sections. 1, 2, 3, 4. So I need to figure out how big are these 4 sections. So I take the period, 2 pi by 3, and I divide it by 4. Well, dividing by 4, that's the same as multiplying by the reciprocal, 1/4. And then I can cancel 2, because it's all multiplication, I can cancel. So 2 over 4 is the same as 1/2. So I end up with 1 pi times 1 in the numerator. That's just pi. And in the denominator, 3 times 2, that's just 6. So it tells me that I'm going to have a key point every pi by 6 across the bottom here. So what I'm going to do, instead of trying to like keep adding pi by 6 and adding fractions and all that, all I'm going to do is take the first number and change it into a denominator of 6. So it used to be pi by 2. I multiplied 2 by 3 to give me 6. So I'm going to take the pi and multiply it by 3. So I'm starting at 3 pi by 6, and now this is the beautiful part. All I'm going to do is keep adding one more pi by 6. So 3 pi by 6, 4 pi by 6. Then one more, 5 pi by 6. Then one more, 6 pi by 6. Then one more, 7 pi by 6. And then just above here, I'm going to actually reduce that to lowest terms, because we wouldn't talk about 4 pi by 6. We would reduce that to 2/3, or 2 pi by 3. 5 pi by 6 doesn't reduce. 6 pi by 6, that's the same as pi. And 7 pi by 6 does not reduce. And there you've got your horizontal values. So remember, this bottom row we are not going to use because it's not in lowest terms. Okay, last step of the box method. I got to decide what kind of curve to draw in here. So it's a sine curve. So I have to think about, is it positive sine or negative sine? Or like in other questions, I'll be thinking about, is it positive or negative cos? So there's 4 choices basically of what I'm going to draw in the middle here. I know that the axis is going to go right through here in the middle. This is a sine curve. So I know it starts on the axis, the middle is on the axis, and the end is on the axis. The regular sine curve goes up and then down. And this is a regular sine curve. It's a positive 2 in front, so it's not going to have a reflection. I'm going to go up and then down. If I saw a negative 2 in front here, I would have to do the reverse, or the vertical reflection of this. So now I've got the first cycle of my graph. I've got the scale all figured out. I just have to add it to my graph. So I know I want to see at least 2 cycles, so there's lots of different ways you can do this. I'm gonna, I see that my graph starts at pi by 2 and goes from there, so I know I don't need to see a lot of negative x values or theta values. I also know that my curve goes up to positive 3 on the y-axis and down to negative 1. So I want to see more positive y's and less negative y's. So there's my scale, or my axes. I'm going to add my scale now. I'm going to label my axes. Notice I've got arrows on the end of my axes. I'm labeling x and y. Oops, I mean theta and y. So for my x, or for my y-axis, I'm always starting there because it's the easier one. I'm going to say every 3 squares is 1. Doesn't really matter as long as you can see negative 1, 1, and 3. And then I'm going to go across. Now, I don't want to label, remember that I knew that I have a key point every pi by 6. Don't count 1 square as pi by 6, or you're going to have like so many key points to draw. So do every 2 or maybe even 3 squares. I'm going to do 2 for the first one. I'm going to go pi by 6 for 1 square. That means 2 pi by 6. And then 3 pi by 6 is pi by 2. I'm reducing to lowest terms as I go. And I'm not going to label every single square. If I've got pi by 2 there, then double that will be pi, and 3 pi by 2, and then finally 2 pi at the end there. And then I can go backwards. Okay, so I've got my scale on there now. I'm going to draw my curve. I know that inside the box, or I can even label the box here. So some people like to do that. Let's do that. So I'm just going to add the box. I know that the box went from pi by 2 going from -1 to 3, and it stopped at 7 pi by 6. So remember, 1 pi by 6 is 2 squares, so 1, 2, 3, 4, 5, 6, 7. There's the end of the box. I can sketch that right on there if I want. You don't have to do that step. And next I'm just going to draw in, and you might also find it helpful to draw the axis of the curve. The axis of the curve was the center of the box, but it's going to go all the way across your graph there. All right, so inside the box we said that we were going to start on the axis, end on the axis, and it's a positive sine curve, so it goes up and then down. And so there's one cycle of our graph. Your job was to draw 2 cycles. Ooh. Your job was to draw 2 cycles. I hope you're having better luck than me. Oof. Anyways, you get the idea. I hope it's probably easier for you on paper, right? And then I'm just going to repeat this pattern. So I see that I have a key point every 2 squares. So I'm just going over 2 squares and adding the next key point. Forgive my computer drawing. This is terrible. Oh my. Okay. And then a key point every 2 squares horizontally. I'm just cycling between the axis, the max, and the mins. There we go, sort of. This is a terrible curve. Okay, and there is our curve f at theta. All right, part C, we're going to complete the chart with the characteristics. So I'm going to start with the parent function, then I'm going to look at our particular example, and then we're going to talk about in general what do the A, K, and D and C do to our characteristics. So remember, our first characteristic was the amplitude. We know that for the regular curve it's 1, the axis is at y equals 0, the max is 1, the min is -1, the range goes from the max to the min. The phase, so notice I've got all my vertical stuff here, and then the bottom of the chart here is all the horizontal stuff. So horizontally, the first one has no phase shift. Woo. I still don't know why that happens. Horizontally, the phase shift is 0 for the parent function. The period is pi, or 2 pi, sorry, and the domain has no restrictions. All right, so what about our function? So you can go and take a look at the graph. And we already kind of talked about this. I've got a vertical stretch by 2. That's going to take my amplitude of 1 and stretch it out twice as far. So my amplitude is 2. The axis of my curve, we talked about this already as well. The horizontal changes don't change the height of my axis of my curve. It's a horizontal line. The stretch doesn't change it, just the vertical translation. And so I'm shifting up to 1. The maximum value is always starting at the axis and adding the amplitude. And the minimum value is always starting at the axis and subtracting the amplitude. So I get 3 and -1. And so here, for this particular function, remember, oops, the order matters. It does have to go from the smallest to the biggest in my range. And also, sometimes people get mixed up and they tell me that the minimum is 3 and the maximum is -1, but that doesn't make any sense. The maximum has to be bigger than the minimum. For our particular graph, the phase shift was pi by 2. And then the period here, remember that we took the graph and we horizontally compressed it by 3. So we took the regular period and we compressed it by 3. So we'll say that the period is 2 pi by 3. What if the k value was negative? Remember that the period, though, is a distance. So a distance can't be negative. So we're not going to divide by -3, even if it was a -3 in the equation. We're just going to take the positive because we're looking at a distance. And then the domain doesn't change. The only time the domain is going to change is if you had like a word problem or a real life example that limited it. All right, so in general, the amplitude of the curve is the A value, the stretch. But again, I don't care if you had a reflection. So we say it's the absolute value of A. We're taking away the negative sign if there is one. The axis of the curve is always y equals the C value. So it's always just the vertical shift. The maximum of the curve is always start at that C value, at that axis, and add the amplitude. Now notice that I'm adding the amplitude, not the A value. So if the A value is negative, I'm making it an amplitude or making it positive first and then adding it to find the maximum. This is where people get mixed up and they tell me that the minimum is bigger than the maximum. Don't do it. To find the minimum value, you start at the axis and you subtract the amplitude. All right, this is going to look messy, but the range is y belongs to the set of real numbers, and then it's going to be the minimum, C minus the absolute value of A, is less than or equal to y, is less than or equal to the maximum, C plus the absolute value of A, and then closing up that set. All right, the phase shift. So in general, the phase shift is D. Notice that in the equation it was minus D, so the phase shift is actually plus D. So up here it was minus D, so the phase shift is actually plus D. All right, the period. The period is normally 2 pi, but we're going to take the horizontal compression, so it's that k value. We're going to divide by the k value, but again, if the k value is negative, I don't care because this is a distance, so divide by the absolute value of k. And again, the domain is not changing unless it's a word problem. All right, next example, example 2. We're looking at sketching the 2 full cycles of the following functions. So same as part B from the last example. We're looking at h at theta. The problem with this equation, though, is that they have the k value here is not factored out. So my first job is to factor out that k value. So to do this, I'm just thinking about dividing it out of each term. So I'm going to do pi by 2 divided by 2. So taking a pi by 2 and cutting it in half, I get a pi by 4. Right? If you have half a dollar and then you divide that by 2, you have a quarter of a dollar. Don't forget you can double check your work by expanding this back out. So 2 times theta gives me back the 2 theta, and 2 times a quarter of a pi gives me a half of a pi. All right, so we're going to draw the box. And we're going to start with the vertical values. So we need the max, the min, and the axis. The axis is where I always start, right? The middle guy, and you can draw in the dotted line if you want. There is no C value here, so the axis hasn't moved. It's a 0. Then to find the max and the min, we need to know the amplitude. Well, the amplitude is the A value here out front. The A value is a half, and so I'm going to add a half to 0 and subtract a half from a 0. Easy peasy for the verticals. Of course, it's these horizontal ones that slow us down. All right, the starting of the horizontal values is always the D value. Notice that that changed, right, when I factored out the K value. So it's plus pi by 4 in the equation, so it's negative pi by 4 on the graph. Now, what do we count by? So here's my K value of 2. So that tells me that the period is 2 pi divided by the K value, or 2 pi divided by 2. So the period now is pi. It tells me that the end of the box is going to be pi after negative pi by 4. So where are all the key points? Remember that there's a key point every period divided by 4. Well, that's just pi by 4. This is a nice gift because we're already in pi by 4s. We just have to keep adding one more. So I had negative 1 pi by 4. If I add another pi by 4, I'm at 0. Add another pi by 4. Add another pi by 4. So now I'm at 2 pi by 4s, and then 3 pi by 4s. Now 2 pi by 4, I can reduce that, right? That's the same as pi by 2. And so I'm going to add this to my graph. These are going to be my scale values. I just have to figure out what's the shape inside the box. So this time I have a cosine curve that tells me that it's either going to start at a maximum or a minimum. It's a positive half out front, so it starts at a maximum. If it starts at a maximum, the end of the cycle is going to end at a maximum. The middle of the cosine curve is the opposite, and then those in between guys are on the axis. So this is what my graph is going to look like, and now I just have to recreate it on the grid. I'm going to pause the video while I do that,